Okay, now let's look at how we can determine empirical formulas based on um, analytical data from compounds. Okay, here's our first example. A 2.651 gram sample of a copper oxide compound is analyzed and is found to contain 2.354 grams of copper, the remainder being oxygen. What is the formula of the compound? All right, so what they're asking for, and they say, what is the formula, right? What they want to know is what is the ratio of the different atoms, right? So we're really asking for either an empirical or molecular formula here. And since this is an ionic compound containing copper and oxygen, ionic compounds are always expressed, or well, are almost always expressed, let's say, as the empirical formula, the simplest ratio of atoms. So what we need to do is determine the empirical formula for this copper oxide compound. And to get the empirical formula, basically that's going to be something like that. We need to know what the ratio, oops, left up my U. Let me do that a little bit better. Right, there we go. So that's really what we're looking for. We want the simplest ratio of copper to oxygen for this compound. So the first thing we can do is use the data that we've got to figure out how much oxygen we've got. The data told us explicitly that we had 2.354 grams of copper, but it didn't say how much oxygen we've got. We can get that by taking the total mass of the compound, and subtracting out the amount that's copper, and whatever's left has got to be oxygen. So let's go ahead and try that. Okay, so if we take the mass of the sample, which is 2.651 grams, and subtract out the amount that is copper, then whatever's left has got to be oxygen. So now we know the mass of copper and oxygen in the compound. All right, I'm going to go ahead to the next slide, so make sure you've written down anything you need from this one, and we'll see how we can use these masses here to determine the empirical formula. All right, so we determined that we have 2.354 grams of copper and 0.297 grams of oxygen. And so this does essentially give us a ratio of a certain type, right? We can see there's about 10 times as much copper as there is oxygen, right? So that's sort of a ratio, but this is a ratio based on based on mass with an S. And to write our empirical or molecular formulas, we need to have that ratio expressed in moles. So the first thing that we need to do is take these masses and figure out how many moles of copper and oxygen we have. Right? So for the copper, just have a little review here. We've got 2.354 grams of copper. We want to know how many moles of copper that is. We can look at the periodic table and find our molar mass, right? The molar mass of copper is 63.55 grams per mole. But if you remember, in a previous video, we talked about molar mass, and we said that this value here should not be thought of as a number, but rather as a relationship. So this 63.55 grams per mole means that 1 mole of copper has a mass of 63.55 grams of copper. And once we have this relationship, since these two things are equal to one another, we can make this into a conversion factor by writing one of these in the numerator This gives us a fraction equal to 1, or writing it the other way, which also gives us a fraction that's equal to 1. So either one of these can then be used as a conversion factor depending on whether we're trying to convert moles into grams or grams into moles. We just have to look at our units and see which way is going to allow them to cancel out correctly. And if we look at this problem, we can see we're trying to go from grams here into moles. So we're going to want to use the second one. Okay. Okay, so I just cleared a little bit of space here. Let's set this up to do our math. 2.354 grams of copper. And then we'll put in our conversion factor. Check to make sure that our units cancel. Grams of copper cancels with grams of copper. And this gives us all right. So this gives us 0.0370417 moles of copper. Now, if this were the end of the problem, if we were being asked how many moles of copper were in this compound, then we'd want to look at the significant figures and we want to round off this result to the proper number of significant figures. Okay, but when we're doing problems where we're trying to determine empirical formulas, everything at the end is ultimately going to be rounded into an integer. So we're trying to find these integer relationships like 2 to 3 or 5 to 6 or 4 to 7 or whatever. So we don't really need to be thinking about significant figures at this stage of the problem. What we want to do with empirical formula calculations is always carry through a few more significant figures than we really should. Okay, and that'll help us to make sure we get to the correct integer ratio. If you round early in an empirical formula problem, you can get really, really bad results. Okay, so in this particular case, we should be rounding this to 4 significant figures, 0.03704, but I would say let's carry this out to at least 37042 or 3700417. Keep just a couple of extra digits to make sure that we get everything rounded to exactly the right point at the end. All right, so this is our number of moles of copper, which we got using the mass of the copper and the molar mass of copper from the periodic table. Why don't you go ahead, hit pause, and then go ahead and calculate the number of moles of oxygen from this number, and then we'll compare our results. All right, so I went to the periodic table and found the molar mass of oxygen, 16.00. Apologize for the handwriting there, that looks a little bit wonky. 16.00 grams per mole. Turn that into a conversion factor and check to make sure that our units cancel out. And I got 18562 moles of oxygen. Okay. And again, as before, we've got three significant figures here. So if this were the problem in and of itself, we'd want to round this result off to three significant figures. But we're not going to do that because for empirical formula problems, we always want to carry extra digits until we get to the very, very end. All right, so what we're trying to get is the ratio of moles of copper to moles of oxygen. And in a sense, we've just done that, right? We've got the moles of copper and the moles of oxygen. So we could almost write the formula for this compound this way. Copper 0.0370,417, oxygen 0.018562. Right? That would actually be showing us the ratio of copper to oxygen, but it's not the simplest ratio. Right? For an empirical formula, we need the simplest ratio, and generally these should be fairly small integers. 1, 2, 3, 4, 5, sometimes 6, 7, 8, things like that, but usually fairly small integer values. So what I'm going to show you next on the next slide is how to take these molar amounts, which are correct, and convert them into the simplest possible ratio. All right, so let's look at that. Okay, once we've got the moles of each of the species in a compound, to get the empirical formula, all we have to do is one really simple trick, and that is to get these two numbers into the lowest possible ratio, we just divide both of these numbers by whichever one is smallest. And if we look at these two, the smallest number is 0.018562, so we're going to divide them both by that number. All right, and for the oxygen, obviously, if we take 0.018562 and divide by 0.018562, obviously we're going to get 1. That's always going to happen. And then for the copper, we take 0.0370417 divided by 0.018562, and what we get is 1.9955. Okay. And this is where these numbers, we hope, are going to come out to be integers. And this is why we need to carry a whole bunch of extra digits through here, right? Because if they come out to integers, they should be really, really close to integers. And you can see here, this is a 1, and this is really, really darn close to 2, right? This is 1.996, right? Really, really close to 2. So that means that our molar ratio is 1 to 2. There are 2 moles of copper for every 1 mole of oxygen, and therefore the formula for this compound is Cu2O. Okay. Now, this is a place where people a lot of times make a mistake. Sometimes people will get results that look like this. They'll get like, let's say, 2.87 and 1.00, and then they just round this to 3 and 1, right? But 2.87 isn't really all that close to 3. If you've done all of your calculations right, and you get to the integers, these numbers should be really, really, really darn close to an integer, to within at least, I would say, about 1%, generally much less than 1% error. If you get 1.92, then you can round that to a 2. If you get 3.04, you can round that to a 3. But if you get something that's off by more than that, say 3.1 or 1.7, 1.8, you cannot round that to an integer. It means that either you've made a mistake somewhere in your calculation, or it means you have a little bit more work to do. And I'll show you how in some cases those results can be converted into integers. So we'll look at a couple of those as well. But the point is, you can only round these to the integers if they're really, really close to whole numbers. Okay, here's a second example. Butadiene is an organic compound composed of 88.82% carbon and 11.18% hydrogen. What are the empirical and molecular formulas of butadiene? Okay. So, a couple things here. This one's different from the other one in two ways. One is it's asking us for both the empirical and the molecular formula for this compound. Last time we only had to determine the empirical formula. And we'll see how to do that at the end. The other thing is that in this case, instead of giving us a mass of carbon, or it was copper last time, but a mass of the two elements in the compound, this time instead we're given a percent. Okay, so the first thing we have to do is figure out how to convert this percentage to a mass, and that fortunately is pretty easy. The first step in a problem like this, when you're given percents, and percent composition are really, really common problems. In fact, if you remember a couple videos back, we took molecular formulas and we used those to calculate the molecular weight, and from that we calculated the percent composition. So what we're doing now is we're just taking that same process and sort of going in the backward direction. We're going, instead of going from the molecular formula to percent composition, we're going from percent composition to molecular formula. Okay. And like I said, these problems are fairly common. You can definitely expect to see these on quizzes and exams, and there are a bunch of them like this in the textbook. So the first thing to do when you've got percents is we'll make an assumption. And again, we can do this because percent composition is an intensive property rather than an extensive property. And because it's intensive, we can assume any amount that we want, right? So let's make the assumption that we have 100 grams of butadiene. If we have 100 grams of butadiene, then we know that we're going to have 88.82 grams of carbon and 11.18 grams of hydrogen. Okay. And so now we've got a problem that's a little bit more similar to the one that we just did with the copper and the oxygen. Now I'm going to go to the next slide and take these masses, the mass of copper and hydrogen, and convert those into moles. If you want, you can hit pause and do that ahead of me, and then we can compare our results and see if we got the same thing. Okay, so I set this up the same way we did last time with the copper and the oxygen. I used the number of grams of carbon and hydrogen, and then I used the molar masses from the periodic table. Then I'm going to check to make sure that I set everything up right by making sure that our units cancel. And for the carbon, when I did that, I got 7.3955 moles of carbon. And for hydrogen, grams cancel, we get moles. It's really important when you're doing hydrogen that you use 1.008 instead of just rounding it to 1. If you do that, you're going to introduce rounding errors, and it's going to make it more difficult when you get to the end. Okay, so always use at least 4 significant figures in all of your molar masses. And when I did that, I got 11.0913 moles of hydrogen. All right, so now we're in the same spot we were in before. We have a molar ratio, right? The molar ratio is 7.39 to 11.09, right? But that's not an integer ratio. So to get this to the lowest integer ratio, divide both sides, or both of these numbers, by the smallest number. Smallest number, of course, is 7.3955. And when we do that for the carbon, of course, this is going to give us exactly 1, right? Because you're taking a number divided by itself, so you're going to get 1. For the hydrogen, when we do this, what I got was 1.4999. Okay. So now we've got a little bit of a problem, right? The whole point of doing this little dividing thing was to try to get these to integer values, and the values that we got instead of integers was 1 and 1.4999, right? Now, like I was saying before, you can't take this and just round it. You can't say the 4999 rounds to 1 or rounds to 2. In order to round it to an integer, it's got to be really, really darn close, okay? But if these numbers aren't integers, right, it means one of two things. Either you made a mistake, so it's possible you need to go back and check your math, okay? Or these are a slightly higher number ratio, and you can get these into the correct number ratio by multiplying by 2 or 3 or maybe 4 or maybe even 5. That's pretty rare. I can't think of many circumstances where you have to multiply by 5. In principle, this could be a larger number, but in the problems that you see, if you have a situation like this, right, you can fix that usually by multiplying by one of these very small integers. And the reason this works is because what these numbers are really is this. You've got 1 here, and this 1.499, right, is really 1.5, right? So your numbers are 1 and 1.5, and you can get rid of this fraction by multiplying by 2, right? Anyway, so let's see how that works. You don't necessarily have to recognize the fraction. Recognizing the fractions makes it a lot easier. But even if you don't, you can just try multiplying by 2 or try multiplying by 3 or something like that and just see what works. So if we multiply this by 2, this is going to give us 2.000. And if we multiply the bottom number by 2, this is going to give us 2.9. Okay, so when I did that, I got 2.9998, right? And you can see that this number now, this number up here is 2, and this number here is really, really, really darn close to 3, okay? So that means our ratio can be described as a 2 to 3 ratio, and so the empirical formula is C2H3. So this is empirical formula. All right, and let's see how we can use that empirical formula to determine the molecular formula. All right, so our empirical formula was C2H3, and we need to know what the the molecular formula was. But unfortunately, we've got a little bit of a problem here because this empirical formula is only the lowest whole number ratio. The molecular formula, remember, sometimes the molecular formula and the empirical formula are the same, so it could be C2H3, but it could also be that the excuse me, it could also be that the molecular formula is C4H6, right? Or it could be C6H9, right? Or it could be C8H12, and so on and so forth, right? It could be, in principle, it could be essentially an infinite number of different possibilities. Right? So if we want to figure out the empirical formula based on, if we want to figure out the molecular formula, excuse me, I don't know why I keep saying those backwards. But if we want the molecular formula based on the empirical formula, we need one more bit of information. Okay. The question as it's posed right now is unanswerable. All you can say is that the molecular formula would have to be one of these, right? And again, continuing on down. But if we have an extra bit of information, so this extra bit of information, the molar mass is approximately 54 grams per mole. Now, what is the molecular formula? And now we can answer it because each of these possible molecular formulas has a specific molecular weight or molar mass associated with it. And all we have to do is calculate the molar mass of each of these different compounds. And I won't go through all the steps there because you've all done this before, but the molar mass of C2H3 is about 27 grams per mole. For C4H6 comes to be 54 grams per mole. And for this one, it's 81 grams per mole. And 108 grams per mole, and so on and so forth. So you don't have to calculate all of them once you get one that fits, right? Obviously, we've got a match there on the molar mass, and so therefore the molecular formula has got to be C4H6. All right, so for these problems, you're given data and you need to determine the empirical and sometimes the molecular formula. The first thing to remember is that the empirical formula is the simplest molar ratio. So you've got to determine the number of moles of each compound, or excuse me, moles of each element in the compound, right? You might be given mass to begin with, you might be given percentages to begin with. The goal is to get that into moles. Okay. If you're given percentages, a good trick is to assume you start with 100 grams of that substance. And if you've got 100 grams of the substance, then you can just change all of the percentages directly into grams. If you had 73% nickel and you assume 100 grams, then that means you're going to have 73 grams of nickel. That makes everything simpler. When you determine the number of moles of each substance, each element, once you've got the number of moles of each substance, divide by the smallest number of moles. Right? Divide each of them by that number to get that to an integer ratio. And you can assume you have an integer ratio if only if those numbers are very, very close to integers. They should be, definitely within 1%, probably about 0.1%. If it's much more, if it deviates much from that, then you may have made a mistake. Or the last thing, if necessary, you could try multiplying all values by 2 or 3 or 4 or maybe 5, but I would say generally speaking, try multiplying everything by 2, 3, or 4. That way, if one of those integers is actually a fraction, like 1 2/3 or 3 1/4 or 1 1/2 or something like that, multiplying by 2, 3, or 4 will get everything back to being an integer. And again, after you do that step, everything should be really, really close to an integer value. If you try that and you're still not close to integers, I would say go back and check your math, because there's probably a mistake in there somewhere. All right, great. There are a bunch of these in the study guide, tons of them in the textbook. So give some of those a try, and we'll be ready for the next topic.